This lecture is about an inductor. This is another two terminal element, but with a different terminal behavior. If we mark the voltage and current across this element uh, such that the passive sign convention is fulfilled, then for this two terminal element called the inductor, the relationship between I and V is something like this. The voltage across its terminals, which is a function of time, is directly proportional to the rate of change of current through it. And the proportionality constant is something that is known as inductance. This is a property of a construction and material that captures uh, this the particular behavior that we are interested in. So inductance, the units for inductance is after the scientist Henry, denoted by capital H, and 1 Henry is a large inductance, but not very large. Like 1 farad was a humongous capacitance, but 1 Henry is large, but not as large as 1 farad. So typically we encounter inductors or inductances of the order of millihenry, a few millihenries, like say 10 millihenry inductor, or even in microhenries, a few hundred microhenries inductors. Basically, the working principle or the construction I will discuss in another lecture. Right here, let me just focus on this relationship. Remember that in the case of a capacitor, we have already seen such a relationship between V and I. It was the current through the capacitor is equal to, or the current through the capacitor is proportional to the time rate of voltage. But here you can see that V has been replaced by I, the I has been replaced by V, and this proportionality constant has changed. So the nature of this expression is similar to this one. So whatever we have developed on this expression can be developed on this the same expression, and I'm not going to follow all those steps to do for this case here. So just like in the case of a capacitor, we have used these two parallel plates to signify that a capacitor is constructed by using two plates that are separated by a dielectric material, and the energy is held within the electric field between the two plates. Charge accumulates on the plates and is separated. There is a displacement current in the dielectric, and so and so. Similarly, we have a science here going on as well. The inductor is formed by making a coil of wire. So it is this is the symbol that we use for an inductor. It is a coil of wire, and it is simple a wire, and there is no breakage in here like in the case of a capacitor. So here the current actively flows through the coil and gets out from the other end. So what this does is actually uh, a few scientists like Michael Faraday and Henry, they independently experimented with this thing, and they came up with such relationships. Faraday actually won, and uh, I think there was some role of the scientist Ampere as well. After which we use the unit for current. The the principle upon which the inductor works will be covered in the second video. But here, let me just expand this into other relationships. So remember, when in the case of a capacitor, we said that I is equal to C dV by dt, we have all set of equations for So when I is related thus as such, the v is related by 1 over c, this integral from minus infinity to t of I t dt. This is the easiest of the relationship. Otherwise, we have this relationship as well. You should equally be knowledgeable about this relationship, that starting from some time t naught up till the present time t, we can solve this integral. Then we should know the state of the capacitor at t naught. So we are finding voltage. This term is voltage. There must be voltage here. So v at t naught. So the voltage of the capacitor at any point t, at any time instant t, would be equal to the voltage at some time instant t naught, which we know. So this may be the initial condition of the capacitor, and then an integral of current flowing in the capacitor since t naught to t. And then we came up with this relationship, that the energy inside a capacitor would be equal to half c v square, or easily written energy is equal to half cv square. By revising this in this lecture for the inductor, basically I intend to shorten the lecture. Whatever methodology we used, starting from this expression to go to this one, to go to this one, to go to this one, can be followed here, and we are going to repeat the same steps. You can see those videos again and be able to find these expressions as well. So the current through the inductor would be equal to 1 by L in an integral from minus infinity to t of vt dt. So mathematics is not concerned with whether this is y or this is x, or this is x or this is y. All the mathematical jargon will remain the same. So we have this expression, or the other expression, it is equal to 1 over L t naught to t vt dt plus the current at t naught. And similarly, the energy contained inside the inductor, here the energy is contained in the electric field between the plates. Here the energy, we will later see, is contained in the magnetic field around the inductor, or say the magnetic field within the inductor. And we are going to get half L I square, or just to remember, omega, the W energy is equal to half L I square. So these expressions are what basically govern the behavior of an inductor and should be remembered. Just as in the case of the capacitor, we also saw that the capacitor voltage cannot suddenly change. Why? From this expression. This expression told us that capacitor voltage cannot suddenly change. Why? Because if voltage has a sudden change in it, suddenly change from one level to the other, the derivative of this sudden change would be infinity, and current has to be infinity, or very large, extremely large, not practical to get this done. So that is why capacitor is used where voltage where we have to stop these changes in voltage, because a capacitor is going to dampen that. And the other thing that we came up with was that uh, when the voltage is constant, that is, it is not changing irrespective of its value. When the voltage across a capacitor is constant, the current through it would be 0. This is again from this expression. So we have the voltage constant, so derivative of a constant is 0, so I would be 0. So these are two very important things that we found from this relationship for the case of a capacitor. Similarly, for the case of inductor, we can just swap these words voltage to current and across with through. We can change voltage to current, any occurrence of the word across with through, because voltage appears across something, current flows through it, and i's with v's and v's with y, and we can get this mm, the equivalent that current through an inductor cannot change. Current cannot change. Obviously it can change, but it cannot change suddenly. Why? Because if we have to achieve this, we would need a voltage across the inductor that is very large, extremely large, that is impractical to get. And the other thing is that if I through an inductor is constant, irrespective of its value, the voltage across the inductor is going to be 0. These are very important uh, behaviors of an inductor and capacitor, and both should be remembered together. So actually, if you remember one of them, the other will automatically be remembered. In the next video, we are going to look at how the inductor works and why it is that we have a coil of wire, and how the energy is stored in the magnetic field. Obviously, we are not going to discuss it in depth, because that is a topic of physics. But from the circuit point of view, circuit analysis point of view, we are going to know a little bit of that.